I'm recording some fresh lectures here for our section on reaction dynamics. And so in this section, this is where we're really going to dive deep and get into these fundamental details that are contributing to kinetics. So the first thing that I want to discuss is collisions and the mean free path. Okay, so we talked about, recall the Maxwell-Boltzmann distribution of velocities. Feels like a lifetime ago, right? But that was at the beginning of the semester. And if you recall here, we came up with equations for the most probable speed, the mean speed, and the root mean square speed. Okay, so as it turns out, the mean speed is adequate for this discussion. Okay, and so what we want to start thinking about now is the relative mean speed between two particles on a collision course. Okay, so I'll write that down here. That's the relative. I'm not happy with how thick my pen is. Let's change that. Okay, there we go. So this would be the relative mean speed. And at this point in the semester, I'm not going to spend a whole lot of time getting into these derivations, but I do want to talk a little bit about where they come from. So for example, suppose we have two molecules, molecule A and molecule B. And we're just going to look at three different orientations that these molecules could be in. So one where they're just traveling parallel to each other, so there's no collision whatsoever. And if they're both at the same temperature and they're both the same mass, they have zero relative velocity between the two of them, right? So it's kind of like one is here and another's here, and they're both traveling along. So zero relative velocity between the two. On the opposite hand, let's say they're both traveling right towards each other at a head-on collision. Well, if B is traveling at velocity v and A is traveling at velocity v, then their relative velocity will be 2 times v, right? And then finally, if there's some average orientation where perhaps they're traveling at some 90-degree angle and collide at that spot, okay, we can break that down into two vectors, right? Motion in, let's say, the left-right dimension and motion in the up-down dimension. And as it turns out, that would end up being root 2 of their respective velocity. And so this, if we wanted to now solve for any angle in between, it gets kind of complicated. However, this ends up being a very good mean or average representation. So that's where we see this expression right here. And we're going to see that come back here momentarily, where the relative mean speed between two any particles is root 2 just times their mean speed. Okay. What we also have to consider now is the reduced mass between the two pair. Okay, so that's reduced mass. Okay. Right when they collide, we've got an A and a B colliding. And so the reduced mass describes that collision pair, which goes as the mass of A times the mass of B divided by the mass of A plus the mass of B. Okay. And then note here all of our units, right? So if I'm using K Boltzmann, right, in joules per Kelvin per molecule, then this mass needs to be kilogram per single molecule. Now, what if I use R instead? So I could do that. I could write this as the root of 8 RT over pi mu. And if that's the case, if I did use R, then instead of doing kilogram per molecule, I would do kilogram per mole. Okay, so let's move forward through this derivation. So now, when we want to start thinking about all of these collisions, we draw this tube here, this collisional tube with area sigma. So I know we just spent some time talking about the absorption cross section. So this is our reactive cross section, okay, or our reaction cross section. So there's not enough letters in the alphabet. So sometimes we have to recycle the same letters. Okay? And so the way this works is we draw some tube, some cylinder, with length c bar relative times delta t, which is in fact what we call the mean free path. So I'll write that as c bar relative times delta t, where the mean free path is the average distance that a molecule travels between collisions, okay, indicated by, if a molecule is outside of this tube, it's a miss, but if it's inside this tube, it's a hit, okay? And that delta t corresponds to the time between collisions. So if we have the mean relative velocity between the two particles and the time it takes for them to reach each other, right, that's going to give us a distance, right? So lambda would be the meters per second times seconds to give me meters, okay? And so now if we zoom in a little bit on what this reactive cross-section will look like. So here in this picture, B has been put in the very center of that cross-section. And as a minimum, so this represents the minimum orientation where A, as you can tell by this picture, would just barely graze by B, okay? So that's the, the minimum orientation, but that gives you the maximum cross-section, right? And so now we notice here that distance, so that's the radius of our cross-section, right? It's a circle, so I'll just note that R and that R are the same. Okay, and we know the area of that circle is pi r squared. Well, that radius is going to be the diameter of A divided by 2 plus the diameter of B divided by 2, right? You can see there's the diameter. Really, so that would be the radius of A plus the radius of B, right? And there's that radius right there. Okay, so that makes up our reactive cross-section. And you can see here Adkins has got some nice calculations for collisional cross-sectional areas. So these are the areas, right, in units of square nanometer. So for example, if you notice nitrogen, that's 0.43 nanometer squared would be that area if I had a nitrogen-nitrogen collision. But now what if I had like a nitrogen-oxygen collision, or perhaps a nitrogen-carbon dioxide collision, okay? Well, I would have to look up the radii of each of those individual molecules, and I could calculate that collisional cross-section for when, A is different than B, okay? And as you might imagine, right, when you look at, let's say, nitrogen and oxygen, they're both very similar, which makes good sense, right, because they're both about the same size. And so if you think about just normal air, right, 80% nitrogen, 20% oxygen, the collisional cross-section between a nitrogen and oxygen will be some weighted average between those two values based on the fact that it's 80% nitrogen and 20% oxygen, okay? So moving forward, so what we want to be able to do is calculate this mean free path, okay? So it starts by recognizing that, this distance, lambda, is going to be c bar relative times delta t, okay? And we can turn that into a collisional area by saying sigma times c bar relative times delta t. So that gives us our collisional area. So in other words, the area of this tube, okay? And from there, we can turn that into a concentration. And that concentration would be, I've got one molecule in this mean free path tube, okay? So the way that this derivation starts is by assuming that this molecule right here is in the tube, and this molecule right here is just outside of that tube because it's going to travel and collide, okay? So now I'll write that our, up here, our number density or our gas phase concentration will be one molecule per sigma times the relative velocity times delta t. Okay, and so let's see, moving forward here. So we also remember that we can calculate our number density, our molecular density, using PV equals nRT, right? So recall we can say big capital N over V equals P over K Boltzmann T, right? So our number of molecules divided by volume is P divided by Boltzmann's constant T, okay? And so recognize that, we said 1 molecule per collisional area, right? But if we expanded that to a much, much bigger total volume, we'll have many of these molecules in their own respective collisional tube. So that means that we can say P, whatever the pressure is, and whatever the temperature is, right, P over kBT, that's going to give me molecules per cubic meter. If I use Pascal and Boltzmann's constant, right, that'll give me molecule per cubic meter. So I'll set that equal to 1 over sigma C bar relative delta T, okay? And let's see, I'll rearrange this to give me delta T, so do some algebra here. So delta T, the time between collisions, is going to be K Boltzmann T all over sigma C bar relative P, okay? And so let's see here. I'm looking at my notes. Okay, great. And so this represents the time between collisions. But what I want to point out here is this assumes that this molecule is not moving and that only this molecule is moving, okay? So when we look back to this, right, I introduced this, the C bar relative is really root 2 just times the mean speed, right? And so in this initial description, it appears as if this molecule is standing still, but it's not, it's actually moving. So we're gonna readjust this, and the time between collisions is kBT times, let's see, let me rewrite that so that the root 2 is in front. So now that's root 2 times C bar times, let's see, I lost my place, times P. Okay, good. All right, let's see, checking to make sure that I'm doing everything correctly. Okay, and so now, if this gives me the time between collisions, then if I take 1 over that number, that's going to give me the frequency of collisions, okay? So let's see here. Yes, so now let's see. If I take 1 over that, so 1 over delta T is going to equal what I'm going to call Z, and that's going to be my collisional frequency, okay? And so I'll write that as Z equals K Boltzmann T, and I'll just keep writing that C bar relative, but we recognize that my root 2 times C bar is the same as my C bar relative, just to keep that in mind there, okay? So now that's, let's see. Oops, I started writing it. I meant to write it as 1 over that, okay? So that's going to be sigma times C bar relative times P all over K Boltzmann T. And let's see here. Yes, that is going to give me my collisional frequency. And so now what about my mean free path? Well, we remembered that up here, lambda is C bar relative times delta T. And I have an equation here for delta T, okay? So what I end up getting is lambda equals K Boltzmann T all over root 2 times sigma times P, okay? So where the C bar relatives canceled. All right, so that gives me my collisional frequency, and that gives me my mean free path. So let's calculate these things.